Hi there, Tasib Ahmed Ashik. I'm currently studying in London South Bank University in mechanical engineering. So today we are going to look at a very important topic in numerical methods, numerical integration and Monte Carlo integration. So when we hear the word integration, we normally think about calculus, but we find an antiderivative and then evaluate it at the limits. But what happens when finding the exact antiderivative, it is difficult or even impossible. This is where the numerical integration comes and it becomes useful for us. So let's first understand the basic idea. So if we look at our mid-ordinate rule, so we might have the area of nth number of rectangles, and we try to approximate of the area under the curve, and it can be deduced to be, if we take 5 strips and we can see there are some heights y1, y2, y3, so on, and we can say there is a distance between two parallel lines, which is D. So geometrically, the integral represents the area under the curve, which is x equal A and x equal B. So imagine we have divided the region under a curve into several rectangles. So if suppose we have 4, or imagine we have 5 rectangles, and the width of every rectangle is D. So the area of one rectangle is simply the width and the height. And for the first rectangle, the height is y1. For the second one, the height is y2, and so on. So the area must be y1 multiplied by d. So therefore, our total area is approximately A1, A2, A3, and A4. So our total area becomes the width multiplied by all of the height, summation of all the heights. So let's take a note, which is the ordinates y1, y2, y3 are all the middle of each rectangle, and the number of strips corresponds to the number of ordinates. So the one important note, which is that while we are taking the rectangle, we are taking extra portion where you can see that there is a curve, but we are taking as a rectangle, so that extra area will be included in our result. So you might take a note that there will be some error in our approximation. So let's take an example. So imagine we have to integrate x cubed between x equal 1 and x equal 2. So our numerical solution will be the height between in the middle of all the rectangles and multiply by width. So these are very common in every term. We take it outside, and if we take a summation of all the d's and all the y1, we find out that our overall total area total will be the width multiply all the heights. So while we are taking all the heights, how can we find out all the heights? So there is a width which we will multiply, which we can find through the difference between the limits divided by number of strips. So the upper limit is 2 and the lower limit is 1, and we will divide by the number of strips, which is 4, and which will become 0.25. Now if we want the height x1, it will be 1 plus d by 2. So the 1 comes from the origin, where we can find here, and to the first parallel line of the first rectangle, which is 1. So there is 1, and the middle point, which will become 0.25, and we have to divide by 2 to take the middle point. So it will be 1, 0.25 divided by 2. So it will become 1.125. And if we put put all the values of xi into the equation, we find out all the results, which is 1.42, 2.6, 4.29. And we will add all the values and we will multiply with the width and we'll find our total value, which is 3.725. And if we do our analytical solution from calculus, we found out that the value comes around 3.75. So you can see the numerical solution gives us a quite very close value of analytical solution. So 3.725 and 3.75 is quite close, but not that close. We can find more close value for our upcoming rule. So it will always have some error. Instead of rectangle, trapezium will minimize the error. The next rule will come right now. So here comes the trapezium rule. So instead of using rectangles, what if we connect two neighboring points on the curve with a straight line? It will make trapezium. And you know the area of all the trapezium is half into the sum of the parallel lines and multiply by the width. So for our first strip, the parallel sides are y1 and y2, and we will add those heights and we will divide by 2 and we will multiply with their width. So the area becomes 1 by 2 y1 plus y2 multiplied by the width, and we will get our A1. So our A total will be d by 2 y1 y2 y2 y3 y3 y4 y4 y5. So finally we will get our formula, which is the width divided by 2, the first height of the strip and the last height of the strip, and we will multiply rest of the heights with 2. So let's take an example. So it says using the trapezium rule, integrate fx equal x cubed between x equal 1 and x equal 2 using 5 strips. Remember that. So here is a curve and we took our 5 strips. So here y1 is 1 and y2 is 1.25 and the width is 0.25. So if we put the value of xi in the equation, we get our all values. And if we put the values into the total equation, it gets 3.7968. So one thing to say is we got our analytical solution from our previous slide, which we got 3.75. So the result goes higher in this rule, which is 3.7968. So take the first value once and the last value and all the values between twice. And you can say that it is an approximation, and in this particular example, it is actually further from the exact answer than the previous midpoint result. So this basically reminds us that different numerical methods have different error characteristics. So if we move on to our next rule, which is Simpson rule. So what that rule tells us. So numerical integration method that estimates the area under a curve by fitting parabolas through the function instead of straight lines. So the basic idea here is very interesting, which is instead of rectangle method and the trapezium method, we approximate it with parabolas. So a parabola is a quadratic curve. You can see the equation of a parabola, which is ax squared plus bx plus c. So 3 points are enough to define a parabola. And the first point is behind the origin, which is my negative side, and the last point is on the positive side. So for y0, we get our point, which is minus d, and y1. So if we put the value inside the parabolic equation, we get our first equation, which is AD squared minus BD plus C. And as we go, we put our M point and N point value into the equation, and we get our rest of the equations. So because the parabola passes through 3 points, we substitute their coordinates. So when we have many strips, the pattern continues. The first ordinate gets a coefficient of 1, and the last ordinate gets a coefficient of 1. So the ordinates in between alternate between coefficient 4 and 2. So you can see here, if we integrate from minus d to plus d into the parabolic equation, we get all the results. From minus d to plus d, we put all the values into the x, and if we integrate it, we found out that the final formula comes d by 3. D is similar as width, and y1, y3 plus 4y2. So what does it tells us? It tells us that for n number of strips, we get our first height value and the last height value. And for even number, we multiply it with 4. And for the odd number, we multiply it with 2. So because of this structure, Simpson rules requires an even number of strips. So let's get to our same example, which is fx equal x cubed. So if we put our xi into the equation, we get all the values for yi, and we put all these value into the formula, and we get our result. So y2, y4 comes for the even, and y3 comes for odd. So in this particular example, the result comes as 3.75, which is a quite perfect estimation, and it gives and you can see that it's very useful. This rule is very useful there than the other rules. So here we move on to our next example, which we will try to use all our methods using 10 strips instead of 5, and we will compare all the results with the analytical value. So we got approximately 3.725 in our previous example from mid-ordinate rule. So now the number of strips goes higher and the width becomes lower, which is 0.1. And if we try to get our first x1, which is the height, we get 1.05. And we try to put all the xi value into yi, and you can see yi is 1 over x. So x is the height, and if we put the x value into the equation, we get our yi. Here is all the yi list from the table. And if we put all the values into the equation, and you guys all know that for the mid-ordinate rule, the equation is a total equal d summation of y. And we get 0.6928. Remember the value. For the next rule, which is the trapezium rule, our table slightly changes because we don't need to divide d with 2, because we take the total width of the trapezium. So if we put all the values into the equation, we get our result, which is 0.6937. So here you can see For the trapezium, it gets 6.6937, and for the mid-ordinate rule, the result becomes 6928. It's quite close. So for Simpson rule, we put all the values. The value doesn't change because we take the whole width. It becomes 0.6932. And as we take our analytical value, here is 1 by x. And the integration of 1 by x is ln x. So we put all the value and we found out our result, which is 0.6931, which is quite close to the Simpson rule answer, which is 0.6932. So you guys can say that Simpson rule is quite similar to our analytical value. So now we can say that from all the rules, we get our most perfect estimation rule, which is Simpson rule. So this is our next topic, which is Monte Carlo integration. So this method becomes essential when you guys can find so many dimensions in the formula or in any equation where normal numerical integration it becomes difficult. So we have been carefully dividing the area into strips, but what if we have the problem? What if we have the problem? It becomes much more complicated. For example, if our integral has many dimensions, numerical integration is very much difficult for higher dimensions. So what we usually do, what usually this integration do, which is it refers to randomly generated points and it tries to calculate areas under the curve. Let's see how we can do it. So here is an example. We want to calculate the function x squared between lower limit 0 and upper limit 1. So if we have the calculus, we can find out our answer easily, which is 1 by 3, which is 0.333, and it will be continuous. So what if we don't know how to do it? We don't know how to do it without calculus. So what if we don't know about calculus? How can we do that? So we randomly throw some points inside the square. Here is a picture. You can see that we are randomly throwing some points into that square. Why we are saying that square? Because it's from origin to 1. So if we square it, it will becomes like that. So we have to factor out the percentage, how many points are under the curve and how many points are over the curve. So points under the curve and divided by total points, we can get the percentage, and we will factor out that number and we will multiply it with 1 and we will get our total area under the curve using points. So imagine we get 3,300 points out of 10,000 points under the curve. So the area becomes 3,300 divided by 10,000 and we will get our answer, which is 0.33. It's not that close to that answer because you can see 333, it's continuous. It will go for eternity. But here we can get our value, which is 0.33. So it's very close to 1 by 3, but not that close. So using this idea, we can simply say that if we put randomly sample points and see how many points fall inside the region, and we can then factor out, and to evaluate the area, we can get our total area under the curve. So why does Monte Carlo work? Because we are essentially using probability to estimate area. So if we randomly distribute points uniformly throughout the square, then every part of the square has an equal chance of receiving points. So therefore, the proportion of points lands into the particular region to approximate the proportion of area occupied by the region. So if approximately 33% points comes under the curve, we can get our total area, we can estimate easily. So let's bring this together. So we already looked at our mid-ordinate rule. That's how we divide the region into rectangles. And for the trapezium rule, we do it using trapezium. And for the Simpson rule, we use it through parabolas. And for our Monte Carlo, we put random points under the curve on the page, and we can see that how many points are under the curve and over the curve, and we can factor out the percentage, and then we try to estimate the area. So this is the main idea behind numerical integration. When an exact mathematical solution is difficult, we can use a smart approximation to get an answer which is sufficiently accurate for our purpose. So thank you guys for watching. Hope to see you guys soon in the next video.